an external magnetic field interacting with a magnetic dipole moment and basically a magnetic dipole moment is a second current. It's basically a representation of second current and representation of orientation interacting with a magnetic dipole moment will cause a torque on the dipole moment in such a way that the dipole moment aligns with the external field. And this is all based on property that our current, or I should say our force, that we have a force between two currents. One current that generates the external magnetic field at our point of observation, and the other current is the current of our dipole moment. Now, let us start looking at a special property of materials, and it is its magnetic properties. And we're going to follow the same type of line of thought as we did in electrostatics. We have a chunk of material, and this chunk of material has many, many different types of characteristics. And we are going to isolate one of those characteristics, and that characteristic is its magnetic property. And we know that the chunk of material is made up of atoms and molecules. And consequently, since we have atoms and molecules, and we have electron clouds around the nucleuses, the nuclei possibly. And as a result, since we have an electron cloud, these charged particles are going to give rise to some type of orbital motion and spin effect. We will only consider the orbital motion in our theory and identify how spin affects the solution of what we have, and when we start talking about different types of magnetic materials near the later end of this lecture. So consequently, we are going to remove all of the material properties and model the material as being dipole moments fixed in space. Since the size of an atom and molecule is extremely small on a macroscopic level, so on the order of, for hydrogen, 10 to the minus 10, for other atoms a little bit heavier than hydrogen, 10 to the minus 9 in value. For a molecule, you can imagine these, depending on the material, these hydrogens and these atoms are going to combine, giving rise to maybe a size that's 5 times larger, maybe 10 times larger. But is very small compared to our measuring instrument. Furthermore, the molecules, the atoms, are fixed inside a material structure. So let us model the motion of our charges as being orbital motions fixed in space. and we can model them by dipoles. Consequently, we now replace our material medium by these dipole moments, or if you like, these special types of currents. And everything satisfies our right-hand rule. Etc. So this was a representation of our dipole moments. And our dipole moments in a zero external magnetic field. So there is no applied field. So this will be our applied field, and our applied field is identically equal to 0. And we will assume that our material is virgin material, that it hasn't been, how would you say, influenced by an external magnetic field ever. So we'll say beginning of time, if you like. And these dipole moments exist in free space. And the magnetic properties of free space is denoted by the permeability of free space. Okay. Now, this is on a microscopic scale. Numbers of these dipole moments are phenomenally large, which makes calculating contributions to the magnetic field at any point inside this material medium too difficult. Therefore, we're going to leave the microscopic level and move towards a macroscopic level where we take chunks of our material to be small in the based on the size of our measuring instrument, but large relative to the dipole moment, so that we can perform a statistical averaging that is suitable to give us an approximate field solution. Consequently, we now break up our volume elements inside our material, or now break up our material in terms of small volume elements. And inside these volume elements are many, many, many